So you're going to need your notes out over nuclear reactions. Probably going to have a periodic table with you also to refer back to. So take out your periodic table as well. What we are going to do is we looked at some examples yesterday of all of the types of nuclear decay. We talked about alpha decay, we talked about beta decay, we talked about positron emission, we talked about electron capture. So we are going to work an example of each one of those before I assign you a worksheet over writing nuclear decay reactions, which is due tomorrow. So, what I would like for you to do first of all, the very first question we have is the alpha decay of uranium-238, which is the most common type of uranium. What I need you to do first of all is I want you at the right below that, and save room because you're going to write two different equations. I want you to write the generalized equation with x's and y's of alpha decay. So what you should have for your alpha decay generalized equation is as follows. AZX will yield A minus 4, Z minus 2Y, and a 4 helium, helium-4. Now, as I am doing this, where do I start? Well, I have the alpha decay of uranium. So I'm going to start out, my X is going to be uranium. Now, as I look on my periodic table, I know, based on my hyphen notation here, that my A is 238. My A is 238. I find uranium on my periodic table. Uranium has an atomic number of 92. So it has 92 protons. As I write my yield sign, I'm first going to do my math. Well, what's 238 minus 4? 234. Last time I looked. 92 minus 2 is 90. What element has an atomic number of 90? Thorium. So my symbol for Y is going to be TH, and then I'm going to finish up with my alpha particle, which is helium. It's that easy. I've just wrote the alpha decay equation for uranium-238. Now, as I look, these numbers, my top numbers have to equal out. 238. 234 plus 4 is 238, correct? 90 plus 2 is 92, correct? So my math works out. I'm good to go. There's the alpha decay of uranium-238. Now, my second step here, cobalt, the beta decay of cobalt-60, which is used in radiation therapy. Go ahead and write your general equation for the beta decay right below that question. As I look at my general equation for beta decay, my A is staying the same. My Z is increasing by 1. Okay? So what does that tell me? Okay, what does that tell me? Well, it tells me in beta decay that I am taking a neutron and it is changing to a proton. So I'm changing a neutron to a proton. Once again, I'm starting out with cobalt. I know that cobalt has a mass number of 60. Cobalt has 27 protons because its atomic number is 27. So when I look over at my math, my A is staying the same. Okay, my Z is increasing to 1. So I've got 60 over 28. What is element number 28? Nickel. So nickel is now my more stable. And here is the beta that is being released. Okay, the beta particle that is being released. Questions on that beta decay there? With the beta particle being released? Good. Here is the third one, the electron capture. So go ahead and write your general equation for the electron capture. We have the electron capture by lead 205 used in insecticides and also in hair dyes. Lead 205, ladies and gentlemen. My generalized equation is as so. So when I'm going from X to Y, when I capture that electron, okay, I have one less proton. So that's telling me that a proton is being changed to a neutron. Because my A stays the same, I am decreasing my atomic number by 1. So once again, lead. Lead is Pb. 205 is my mass number. My atomic number for lead is 82. When I capture that electron, it'll give me that same 205 because my A doesn't change. 82 minus 1 is 81. Element number 81 is thallium, Tl. Thallium is Tl. And I also have a release on this one of some gamma rays. So that's why when we talked about alpha particles, beta particles, and gamma rays, these are some gamma rays that will be released with this also. But there's my equation. Does my math add up? 82 minus 1 is 81. It's got to be the same on each side of my arrow. Does indeed match up. Now the final example I'm going to work, we've done all except positron emission. So the positron emission by oxygen 15, which is used as a tracer in the measurement of regional blood volume and blood flow. Go ahead and write the general equation that you should use for the positron emission. And when we did so, we came up with this equation. So we look at that. I see my generalized equation. Okay. Once again, I am losing a proton from X to Y. So we are taking a proton and it is being changed into a neutron. Okay. So, oxygen 15. Okay, oxygen 15. Oxygen has an atomic number of 8, so it is 15 over 8. My mass number is going to stay the same. 8 minus 1 is 7. Element number 7 is nitrogen. And then I have this positron. Okay, this positron that is being released. So those are the 4 basic types of nuclear decay that we will be dealing with in here. Do we have any questions over those? Like I said before, probably the best thing to do is memorize this generalized equation right here for each of the 4. Okay, memorize that generalized equation for each of the 4, and these things should be pretty easy for you folks. Any questions for me?